Next term is a cut vertex. A single vertex whose removal disconnects a graph is called a cut vertex. It is also called as articulation point. Whereas when we remove an edge from a graph and you are getting a disconnected graph, that edge is called as a cut edge. It is also called as a bridge. For example, we need to find the cut vertex and cut edge for this graph G. If you remove a vertex A, whether it disconnects the graph, note that when you remove a vertex from a graph, it means we will remove the incident edge with that vertex. For example, if you remove this vertex A, it means we need to remove this edge AB. Now the point is this graph is disconnected. So answer is no. This graph is connected one. So therefore A is not a cut vertex. Next, if you remove a vertex V, it means we need to remove the edge AB as well as BD and BC. So after removing the vertex V, you will get this graph. Now whether this graph is disconnected, so answer is yes. It means B vertex is a cut vertex. Now what about the C vertex? Whether C is a cut vertex, so let's remove the vertex C. Is this graph is disconnected? So answer is yes. It means C is the cut vertex. Next is a vertex E. So if you remove a vertex E, after removal of these edges, whether the graph is connected, so answer is no. So we are getting a disconnected graph. Therefore E is a cut vertex. F. So remove the vertex F and the corresponding edges. Whether it disconnects the graph, so answer is no. It means F is not a cut vertex. Now what about the vertex G? So either this disconnects the graph, so answer is no. It means G is not the cut vertex. Now what about the H vertex? So if you remove the H vertex and the corresponding edges associated with the vertex H, whether this disconnects the graph, so answer is no. It means H is not a cut vertex. Now we need to find the cut edges in this graph. So for that we just need to remove the edges and we need to check whether the graph is disconnected one or not. So after removal of any edge, if the graph is disconnected, that is called as a cut edge. So let's try to remove the edge A and B. So when you are removing an edge A and B, make sure the vertices should be there. We will not remove the vertices in this case. So after removal of the edge AB, we are getting a disconnected graph. We cannot reach from a vertex B to A. So it means AB is a cut edge. Now what about the BD edge? So if you remove the BD edge, whether it disconnects the graph, so answer is no. So it means BD edge is not the cut edge. So now what about this edge between a vertex B and C? So after removal of this edge, whether it disconnects the graph? So answer is no. It means it is not a cut edge. DC. So removal of a DC edge. Again we are getting a connected graph. It means this edge is not a cut edge. So if you remove an edge CE, so now we are getting a two different connected component, means it is a disconnected graph. So next cut edge is CE. Now what about this edge FE? So if you remove this edge, we are getting a connected graph. It means this is not the cut edge. So after removal of this edge, again we are getting a connected graph, means this is not a cut edge. So after removal of this edge, again we are getting a connected graph. It means it is not a cut edge. So after removal of this edge, again we are getting a connected graph. It means it is not a cut edge. So after removal of the edge EH, again we are getting a connected graph. It means it is again not a cut edge. So in this graph we have 3 cut vertices and 2 cut edges. Note that not all graphs have cut vertices. For example, for the complete graph with n greater than or equal to 3, where n represents the number of vertices, has no cut vertices. Let's take an example for the K4 graph. So this is the complete graph with the 4 vertices. Now in this case, identify the cut vertices. So if we remove a vertex V1, it means we need to remove the edge V1, V2, V1, V3 and V4. Still the graph is connected. In that case, you are getting a subgraph of this form. Now this graph is the connected graph. Similarly, if you remove V2, again you will get a subgraph of this form, and still the graph is connected. And if you remove the V3, so you will get a triangular form between the vertex V1, V2 and V4, and still the graph is connected. And same for the V4. So in this case, we are not getting a single cut vertex. And such graph is called as a non-separable graph. A connected graph without cut vertex is called as a non-separable graph. Next is a vertex cut. It is also called as a separating set or a vertex separator. So what do you mean by vertex set? It means we need to collect the subset of a vertex in such a way that when you delete that subset of vertex from the original set of vertex, it disconnects the graph. For example, take the cycle of the length 4. So in this case, if you remove these two vertices, when you're removing a vertices, the corresponding edges are also removed. So then we will get the disconnected graph. In that case, this subset is called as a vertex cut. For example, so in this case, we need to find the vertex cut if it is there. So in this case, if you remove the vertex B, so with this we will remove the edges. Now, whether by removing a one single vertex, it disconnects the graph. So right now, no. So let's try to remove some another vertex. So if you remove the vertex A, still you will get a connected graph. If you remove the D vertex, let's try to remove the vertex D. Now, is this a disconnected graph? So answer is no. Next, if you remove E vertex or F, so definitely you will get a disconnected graph. So let's suppose we are removing the vertex E. With this, we are getting a disconnected graph. It means in this graph, the vertex subset B, D, E is called as a vertex cut. So the next term is a vertex connectivity. Vertex connectivity of a non-complete graph G, it is denoted by kappa of G, and it is calculated as minimum number of vertices in a vertex cut. In the previous example, we have observed that the total number of vertices in a vertex cut is 3, and that is the minimum count. Therefore, the vertex connectivity of previous graph is 3. And in cycle C4, the vertex connectivity is 2. Just by removing the two vertices, you will get a disconnected graph, and that is the minimum number of vertices we are removing from the vertex set. Therefore, its connectivity is 2. Next is a edge cut. So by removing enough certain edges from the given graph and we are getting a disconnected one, then that set of edges is called the edge cut. So when you are removing a single edge from the graph, it is called as a cut edge. And if you are removing more than one edges from the graph to disconnect it, that is called an edge cut. So in this case, if you remove any single edge from the graph, then you will not get a disconnected graph. So let's try to remove more than one edges in this graph. So if you remove an edge A to B, whether this disconnects the graph. So answer is no. So if you remove A to E edge, still we will find a path between each and every vertex. And if you remove next edge AD, now we cannot reach to the vertex A by starting from any of the vertices from here. So it means now this is a disconnected graph. First we will take edge cut as by removing an edges AB, AE and AD. Another possible case can be if you remove this edge B to C, and next edge if you remove this one CD and remove this edge CF. Now you can check it disconnects the graph. We will keeping these edges but we are removing these lines. So with this it disconnects the graph because right now C is an isolated vertex. So this is also a edge cut for the given graph G. So next is edge connectivity. Edge connectivity means the minimum number of edges used in a edge cut to disconnect the graph. So in this case, we have observed the minimum count of edges required to remove so that we will get a disconnected graph is 3. So therefore, the edge connectivity for this graph is 3 and it is represented by lambda of G. So in this case, lambda of G is equal to 3. Next, we have a result for the relationship between the vertex connectivity and the edge connectivity, but for the non-complete graph. Why we are working with the non-complete graph? Because we have studied that the complete graph is a non-separable. Therefore, this inequality is only for the non-complete graph. So it says that the vertex connectivity of a graph is always less than equal to the edge connectivity of a graph, which is further less than equal to minimum degree vertex from that graph. Question of the day. So find the vertex connectivity and edge connectivity for this given graph G and comment below the answer for the vertex connectivity and the edge connectivity. Also, you can verify the inequality between the vertex connectivity, edge connectivity and the minimum degree of the vertex in a graph G.